Welcome to this podcast. In this podcast, we're going to talk about information from Chapter 2. Chapter 2 deals with the chemical complexity of life. And your book begins talking about this with the term matter. This term is often introduced to us in a chemistry course, meaning anything that takes up space. A rock, a book, a chair, a house, all of these things take up space, and they would all be matter. However, we also have to remember that matter is also living things, since living things also take up space. And if you remember a podcast ago, maybe 2 podcasts ago, we talked about the levels of life. We talked about going from a simple atom all the way up to the cell, to an organ system, to the organism, and then we carried that on out further throughout the ecosystem. But let's talk about the organism again. And I want to show you this picture here. And this picture is a picture of my 3 boys and their dog. These all take up space, so they are all matter. But what makes them up? What ultimately gives these boys and this dog matter and allows them to take up space? Well, remember we said each of these organisms here, it's kind of weird calling my children these organisms, but they are. Remember, if we broke this down, these organisms, they're composed of organs and the organ systems. These organs then are broken down into tissues. These tissues are broken down into cells. And then when we get below the level of cell, now we start getting into the area of things that are not alive on their own. So like organelles, or other cell parts. These organelles then are made up of something called macromolecules, and we're going to talk about macromolecules later on. But for now, just know macromolecules are things like DNA, proteins, fats, carbohydrates. What makes up these macromolecules then? These macromolecules then would be made up of compounds. A compound is something that is made up of 2 or more elements. They are not random elements. They are very fixed elements. For instance, you might think of something like water. H2O is a compound. It's a very fixed ratio of hydrogen and oxygens that make up that compound of water. And then below compounds, now these compounds are further broken down into elements, which isn't too surprising since I just told you a compound is 2 or more elements. Now these elements you might remember from your periodic table from a chemistry class. Now an element is the simplest structure that cannot be broken down by a chemical reaction. Some examples of elements would be hydrogen, oxygen, silver, potassium, etc. There are 92 of these elements. Now these elements are composed of atoms. Now atoms, for now, just remember they are the smallest components of an element that still retains the properties of that element. I'm going to erase atoms here because I'm going to spend a little bit of time talking about elements. Of these elements, of these 92 elements, about 20 to 25% of them are essential. These essential elements are elements that an organism requires to sustain life. So as I said, there's about 25% of these 292. Now, interestingly, it's not the same 25% for each organism. For instance, as your book points out, humans, we have 25 elements that are essential elements. However, plants only have 17 elements that are essential. Now you may find other elements in an organism. It's just that these are the essential ones. Okay, let me erase the examples of humans and plants for now to give me a little space here. So I'm going to talk about the 4 major essential elements, the ones that make up the largest amount of the essential elements. Doesn't necessarily mean they're more important. It just means that of these 25% essential elements, these 4 are the major ones. They are oxygen, carbon, hydrogen, and nitrogen. You need to know these four, and you need to know that together they make up about 96% of all the elements in our body. You don't need to remember the individual components of each of these. All of the other elements that aren't these major ones we call trace elements. Still very important and still required, so they're still essential, but they're required at a much lower concentration. Some important trace elements include calcium, iodine, phosphorus, potassium, sulfur, and magnesium. Now, before we move on to the next whiteboard, I want to stress an important point here. And this is a point that's a little mind-blowing, I think. When we look at all these organisms in this picture, the boys, the dog, and the grass, I didn't mention the grass before, but certainly that is an organism. Everything that they are, as you move down this chain here, is ultimately because these elements came together in such a unique way to give rise to compounds, to give rise to macromolecules, to organelles, to cells, tissues, the organs and their systems, and ultimately to these organisms. It's the basic fundamental elements and the atoms that make up these elements that ultimately give rise to what we see here in this picture. Let's go ahead and erase this board and move on to spending a little bit of time talking about the atom. Okay, I want to spend a little bit of time now talking about atoms. We primarily focus on atoms in the physical sciences. We think about them in chemistry and physics class, but ultimately, as I hope I conveyed on the last slide, that atoms are really important to understand as we try to understand life, because ultimately all of life consists of these atoms, which then go on to make elements, which are then essential to make organisms. Now we can think of an atom, just as a brief definition, as the smallest unit of matter that still has properties of an element. And because of that, when we think of the element, say carbon, which is abbreviated as a C, the atoms that make up carbon we also abbreviate as C. And though this may be review for some of you, I want to take a few minutes and talk about what makes up this atom. And I'm going to draw kind of a dotted line here, or circle. On the outside of it, on this dotted line, are the electrons. Often in the semester when we want to talk about electrons, I'm just going to draw it as an E minus. Now in the middle here, I'm going to draw it as a square, is the nucleus. So over here I'm just going to draw a square, and that equals nucleus. Within this nucleus are protons and neutrons. I'm going to show the protons as plus signs and the neutrons as equal signs. So the nucleus, I would write down here, contains protons. So the nucleus down here contains protons and neutrons. Neutrons, if you think of the first part of this word, N-E-U-T, they have a neutral charge. So let's go ahead and write that down here. Whereas the protons have a positive charge. Now it's sort of hard to represent here, and for what it's worth, I wanted to make one more point to you. And that is that in relation to the space of the atom, the nucleus is really small. So small that the distance between the nucleus and the electrons is huge. I think your book says something on the lines of, if the nucleus was the size of a baseball, the electrons would be 4 kilometers away with nothing in between them. So in relation between the space between the nucleus and the electrons, it is a vast open space. Now in chemistry, you're going to spend a lot more time talking about electrons and neutrons and protons and all that good stuff. But I want to just point out a few more fundamentals of how we're going to use these numbers. And so I'm going to erase a lot of this, and I'm going to focus on the element of carbon. And focusing on carbon is not by accident. Carbon is a critical element for anything that is organic. So we often will see the atomic number written up here. And for carbon, it is 6. So the atomic number is equal to the number of protons. So carbon has 6 protons. C, in this case, as I mentioned before, but just to make it clear, the abbreviation for the element is written in the middle here. So carbon is equal to C. Underneath this symbol of carbon, we often see another number. And for carbon, that number is 12.0107. And this is the atomic mass. And this is equal to the number of neutrons plus protons. Another thing I want to write down here, it's an important thing to know, an uncharged atom is when the number of electrons equals the number of protons. When this happens, there is no charge to the atom. So let's take that knowledge and answer a question. Let's say we're dealing with the element of sodium. That's abbreviated Na. We know that the atomic number is 11 and the atomic mass is 23. And if the question is, now answer the question, how many neutrons are there? Well, we know the number of protons is 11. So we have 11 protons. We get that from the 11 up here. We know the mass is 23, and so we know that the mass is the number of protons plus the number of neutrons. So the number of neutrons has to be 23 minus 11, or 12. Now this problem should have been worded slightly differently. I should have said how many neutrons are in an uncharged sodium. If it was charged, the answer could be different. On an exam, I will only deal with uncharged atoms. When you take chemistry, they'll probably throw some charged atoms at you. Another one that I'm going to let you work on your own, just to practice. Okay, as practice, let's look at an additional problem. Let's look at one of the favorite elements, krypton. It has an atomic number of 36 and an atomic mass of 84. Looking at this, you should be able to tell me the number of protons, the number of electrons, and the number of neutrons. And what I'd like you to do is to hit pause on this tape and answer these questions and then hit play again. Okay, hopefully you figured out these answers, and welcome back. The number of protons, remember, is always going to be equal to the atomic number, which in this case is 36. Now, the number of electrons is easy to calculate if I tell you that this is an uncharged atom. You can assume it's uncharged unless it's stated otherwise. And if it's an exam, I can tell you now it will always be uncharged. If it's uncharged, we know that the number of protons is equal to the number of electrons. So the number of electrons will also be 36. To get the number of neutrons, we subtract the number of protons from the atomic mass. Because remember, this number is the protons plus the neutrons. So 84 subtract 36 is 48. There's bound to be a question like this on the exam. So make sure you understand it at this level. I want to define a couple other terms for you. The first is isotope. Isotopes, I think we can basically define as different forms of the same isotope. Of the same atom. As we see atoms in nature, they don't all look the exact same. They can come in slightly different forms. So let's look at carbon as an example. Carbon-12 is the most common form. Carbon-12 has 6 protons. It also has 6 electrons and 6 neutrons. So it has a mass of 12. Because remember, the atomic mass is the number of protons plus the number of neutrons. However, carbon-13 still has 6 carbons and 6 electrons, If we change those, then we have a different element. So these are still carbon, but the neutrons change. In this case, we have 7 neutrons. And so now the mass will go up to 13. You can look at carbon 14. I'm just going to put C14 because of space. It has 6 protons, still 6 electrons, but now it has 8 neutrons to give us a mass of 14. All of these are carbon, but they form different isotopes of carbon. Let me erase this, and I'm going to just briefly tell you what a radioactive isotope is. Now let's talk about radioactive isotopes. Now remember on the last slide, I said every atom exists in different forms, or what we called isotopes. These isotopes within any given atom have different types of stability. So for instance, in carbon 12, the natural form, or the most stable form I should say, so I'm going to say most stable. And with that, we also have isotopes, say, of carbon 14, which is the least stable, or less stable than 12, I should say. And remember I said we call these still both carbon because the number of protons don't change. But the moment the number of protons changes, that atom becomes a different atom. And that happens because of spontaneous decay. Just over time, the stability of these atoms changes, and they begin to lose protons. And now when that happens, we will see a new atom. Carbon 14 often decays to nitrogen, another element. That's all you need to know about radioactive isotopes. Alright, that's all I have for this podcast. There will be another podcast for day 4 that will cover how molecules and compounds are formed, and also talk about cellular reactions. If you have any questions at all, please make sure you come see me. If not, I'll see you in class. Bye.